All right, so let's do what we always do. Let's greet each other properly. Good morning.
Good morning.
This is Mr. Ainsworth, and we're going to get into two main theorems in calculus called Rolle's theorem and the mean value theorem. They're related, and since the mean value theorem is a generalization of the Rolle's theorem, let's start off with the Rolle's theorem. Let's define it first. Take a look at what it means graphically and show you how to apply it. Okay, so let's start off with me up here. Let's define it first. Let's say, let's let f represents our function here, be differentiable on the open interval. So let f be differentiable on the open interval. Okay, now remember, when I say open, I'm talking about an interval on the x-axis from one point to the other. Let's call it a to b, okay, which does not include the endpoints. So open includes all points in between a and b, but not including a and b. Okay, it's a little bit different than closed interval. So it's differentiable on the open interval from a to b, and continuous on the closed. And continuous, let's see if I can spell it, on the closed interval from a to b. And the way you write a closed interval is using the square brackets. And by closed interval, I mean that all points from a to b, including a and b. So closed is different than open, okay? Closed includes the endpoints and open does not. So let's review what we just have so far. F is differentiable on the open interval from a to b. Remember, that's just from 1 point to the next on the x-axis. It could be from 2 to 5 or from -1 to 7. It could be anything. And it's continuous on the closed. If that's the case, okay, then Rolle's theorem states the following. It says, if f of a equals f of b, those are function values now. That's the function evaluated at a. That's a y value. If that's equal to f of b, which is another y value, okay, then what Rolle's theorem states is this. Then there exists, okay, at least one point C, at least. Now what does that mean? At least means one or more, okay. At least one value C, or 1 point C, we'll call it just C in general, okay, in the open interval from A to B, so it has to be inside there. And we're going to have to check that in the problem, okay, it has to be inside the interval from A to B, all right, such that f prime of C is equal to 0. Now in all theorems in calculus, they're pretty ambiguous at the beginning, especially if you don't have the graph. And it's hard to understand sometimes without the graph. So let's go off to the side and let's draw a simple situation to interpret what in the world this means. And then I'll show you how to apply it, because the application is fairly straightforward, and actually the geometric interpretation is too. So let's go ahead and just draw a little simple sketch of what I'm talking about here. Okay, so suppose we have the x and y axes over here. And let's just put a function in here. I'm going to just draw it in red. So there's our function f there. It could be any function, by the way. But it has to be differentiable on the open and continuous on the open interval or on the closed interval from a to b. So check this out. Let's suppose that this point right here is a, and over here this value is b. So those are values on the x-axis. A could be 1 in this case, and b could be 10. So our interval could be from 1 to 10 in this case. And if you look at a here, if you go up to the function and move left on the y-axis there, we call that f of a. So who sees that f of a is actually the same height or the same value as f of b? Who sees that? F of a and f of b are the same. Okay, let's write that down. It's equal to f of b here. Okay, now notice in the theorem here, it says if f of a and f of b are equal, there exists one c. And where's c? There exists at least 1 point C in this open interval. That means between a and b. Okay, so c has to be between a and b, so it's got to be in here. Okay, in here, such that f prime of c is equal to 0. And again, recall what in the world does the derivative represent in general? The slope of the tangent line, right? So here, this f prime is equal to 0. It's a statement saying that the slope of the tangent line right here at C is 0. And what kind of line has a 0 slope? Okay, so what this is saying is that there's, at some point C in between A and B, there exists a horizontal tangent line to the graph. And who sees one right now up there? And guess where it exists? At the max, at the relative max up here. Okay, so let's plot that. So right about here. In this case, C is right here. And it's a horizontal tangent line at that point. And f prime at C is equal to 0. It's a horizontal tangent line. So what Rolle's theorem is saying is that if you start off with a differentiable function on the open interval, it has to be differentiable, which means there can't be any cusp in there. There can't be any corners, cusps, vertical tangent lines, things like that nature. It has to be differentiable. It also has to be continuous, which means there can't be any holes or jumps, things of that nature. So if it's differentiable on the open and continuous on the closed, which means it's continuous everywhere from A to B, continuous everywhere, all right, then there exists that C value, and C is just some real number, which we're going to have to find, such that the f prime, the derivative evaluated at that point, is 0, which means that we have a horizontal tangent line at C. Okay, that's what it means. So, well, why is it important to be differentiable, and why is it important to be continuous? That's what I'm saying right here. Notice both conditions are necessary. In any theorem in calculus or any part of mathematics, if the hypothesis has to be met. If it's not met, the theorem's not true. So one of the things you're going to have to do when you apply the Rolle's theorem and the mean value theorem is make sure the hypothesis is met. You're going to have to prove it. And once it's met, then you can apply it. Because you can't apply it if it's not true. Does that make sense? Okay. So why are both conditions necessary? Because I said without either one, the statement could be false, or probably is false. Okay, so if it's not continuous, it's discontinuous. So let me give you a case right there. Let me show you what happens if you have a discontinuous function. So let's draw a little picture of it. Okay, if it's discontinuous, you may have a jump, or you may have a hole, in which case you might have something that looks like this right here. Okay, so there's F. F is in blue right there. And let's suppose we're talking about from A to B here. So there's A. Okay, it looks like it's continuous everywhere, but let's suppose B is right here. So you guys see the jump at B? Okay, it's discontinuous. There's a break in the function right there at B. And if you consider such a function here, try to find a horizontal tangent line somewhere along the graph. Like look right here. If you go from A to B, move along the graph right here. I mean, if we drew the tangent lines, it would have positive slope, positive slope, positive slope, positive slope right here. And it would be impossible all the way up into the open point here at B to draw a horizontal tangent line. Who sees what I'm talking about? Okay, so if the function is discontinuous somewhere from A to B, either at the endpoints or somewhere in the middle, there may not be a horizontal tangent line. So the theorem won't apply. So it has to be continuous everywhere on the open interval, even on the endpoints. It has to be continuous. It has to be continuous. So how about a continuous function but non-differentiable? So if it's continuous enough differentiable, there may be a what somewhere? A cusp or a corner, right? Okay, because we know it's not differentiable at a cusp or a corner. So in which case you might have something that looks like this. So let's draw a picture of that. Okay. So it might be something that looks like this. Okay, so there's our function right there. We have a cusp at C. So it's non-differentiable there. All right, and if you attempt to, oh, by the way, who notices that it's continuous everywhere? It's continuous everywhere. Okay, you can trace that function with a pencil without lifting it up off the paper. Okay, so it's continuous. But there's a cusp at C. And as we talked about in prior chapters, that functions aren't differentiable at a cusp or a corner. So it's non-differentiable there. You might want to make note of that. It's non-differentiable at C because of the cusp. And if you try to draw a tangent line at any point on the function, I put it in red. If you try to draw it at like somewhere like right here, Okay, it's going to be a tangent line, but it's going to have positive slope. Even if you go to the right of the cusp, the tangent line is going to be, if that's f prime there, this is f prime. It's going to have negative slope. You can do that at any point in between A and B, and you will not be able to draw a tangent line that's horizontal, that has zero slope. Who sees that? Who's with me on that? Okay, you could try to draw it anyway. It's just not going to happen. All right, even at C, it's not going to happen. You can't do it at C. There's a cusp there. So it has to both be continuous on the closed, which means continuous everywhere in the interval, and it has to be differentiable in the open interval, which means differentiable everywhere between A and B. If those conditions are met, then Rolle's theorem applies, and you can find C where there exists a horizontal tangent line. Okay, and that's our job today. That's part of it. That's on Rolle's theorem. So let's go ahead and let's apply it. Let's take a look at a real function here. Okay, and the very first thing we need to do, look at part A, is that we're given this quadratic function here, which, by the way, what's the special unit we use for quadratics? Starts with a P? Polynomial. Not polynomial, but parabola. Okay, those U-shaped functions that we ground, right? F of x equals x squared minus 2x. It's on the closed interval from 0 to 2. That's called a closed interval there, which means what? Includes endpoints or not includes? Includes. Okay, it's closed. First of all, we need to determine where the Rolle's theorem applies, and if so, find C in the open interval such that f prime of C equals 0. Okay? So we got to talk about, is it continuous? And I've talked about this before. That's a polynomial, yes? What do we know about all polynomials? Okay, they're continuous everywhere. So let's write that down, part A. And by the way, on your IB exams and your AP exams, it doesn't matter which route you're taking, AP or IB, when you take your exams, they're going to have you explain things, okay? And they're going to grade you based upon your explanation. And so it's really good practice to do this because you're going to have to describe why this is applicable in words, okay? So simply here we got a polynomial. This x squared minus 2x is a polynomial, and we know that all polynomials, okay, are continuous everywhere. You can just simply state that. If they're continuous everywhere, then they're certainly continuous from the closed interval from 0 to 2. That's good. Okay. How about differentiability, though? It has to be differentiable on the open interval from A to B. So polynomials. Do polynomials are they differentiable everywhere? I see a yes back there. Are polynomials, aren't they smooth? They may go up and down, like cubics go up and down, quartics, go up and down. But are they smooth everywhere? Yeah. They sure are. Do they contain any cusp or corners? No. So are they differentiable everywhere? Yes. We can just make a general statement from now on. So we can say continuous, and let's abbreviate here, and differentiable everywhere. Okay? That satisfies the Rolle's value theorem, and now what we need to do is find C such that f prime of C equals 0. So what we need to do is take a derivative. Okay? So let's differentiate. So this is part B. We have to do this part right here. We got to find C such that the derivative is equal to 0. And it has to be inside or in between A and B. So f prime, what's that? Tell me what it is, guys. Okay, 2x minus 2. So f prime is 2x minus 2. Set that equal to 0 to find C. Okay? Where C is inside the interval there. Okay? So what's the obvious answer there? What's x equal to? 1. X is 1. Now, look in your interval. Look here. Okay? 1 has to be between 0 and 2. It has to be in the open interval, not the closed. So not the endpoints. It has to be inside or in between 0 and 2. Is it? Yeah, obviously, 1 is between 0 and 2. So we'll just put in 0, comma 2. That means in the open interval from 0 to 2. So therefore, C equals 1. So all you have to do is take a derivative, set equal to 0, and solve that equation. So it's really not hard to do. And then the last thing you need to do is check to see if C is in the open interval. And if it is, you found C. If it's not in there, because sometimes there are 2 or 3 values. If you find more than one C value, because remember it says there exists at least one, which means 1 or more. So if there's 1 or more, or like 2 or more, then just take the ones that are inside the open interval, and those are your values of C. Okay? Questions up to this point? Pretty straightforward? Yeah. All right, let's try it again. Go ahead and work on, I'm going to pause the video. Find f prime. Well, actually, wait a minute. We've got to see if it applies. So I'm not going to stop video here. Let's go We got to talk about whether it applies first. Okay, so we got x to the 2/3 power minus 1. X to the 2/3 power minus 1. First of all, is that continuous everywhere?
No.
To answer that question, is it undefined anywhere? It's a domain question, actually. Is x to the 2/3 power minus 1, is it defined everywhere?
Yeah.
Can you take any number to the 2/3 power?
Yeah.
That means square it and then cube root it?
Yes, you can.
Okay, if you can't, then what number can you not do that with? Oh, okay, maybe square roots, you mean?
Yeah.
Okay, yeah, okay. Well, we're just talking squares, right? You can take anything to the second power, then cube root it. No problem. Okay, so here the domain is all reals. So it's defined everywhere. And if it's defined everywhere, it's got to be continuous everywhere. So this right here is continuous everywhere. And by the way, if you weren't sure about that at home and you're doing this by yourself, what could you do?
Calculator.
Graph it on the calculator and take a look at it, right? So it's a domain question. Since it's defined everywhere, it's continuous everywhere. You can verify that on the graph if you want, okay? So it's continuous everywhere. Everywhere. Okay, and it has to be differentiable too. Now, to answer that question, you have to evaluate the derivative. Okay, so let's get the derivative right now. So f prime. Okay, so power rule. So we got 2/3 times x to the what? Negative 1/3, and then the derivative of negative 1 is just 0. And now you got to rewrite this. And 2 divided by 3 times x to the 1/3. There's your derivative. Okay, let's stop here. Let's figure out, is it differentiable everywhere? Yes or no?
No.
Use your hands. Yes or no? Okay, most of you are saying no. Then tell me, where is it not differentiable?
0.
Very good. It's not differentiable at 0. There's a cusp there. Okay? It's not differentiable at 0 because the derivative is not defined at 0. Right? Let's write that down. So not, or you can say non-differentiable. Not differentiable at x equals 0. Right there. You could say, the derivative is undefined there, or you can say it's non-differentiable there. They mean the same thing. And but the theorem, let's go back up to theorem. Let's read the very top. Up here, guys, read with me. F must be differentiable on what? On the open interval from A to B. Is it? Let's go back to the problem. The open interval is from negative 8 to 8.
Yeah.
So,
Yes. No.
so from negative 8 to 8, is 0 in there?
Yep.
All right, so right there, it's 0 is inside the open interval from negative 8 to 8. So right there, it's not differentiable in the open. So f is not differentiable in the open interval from negative 8 to 8. In negative 8 to 8. Because 0 is inside there, guys. So it's continuous everywhere, but not differentiable in the open. So does Rolle's theorem apply or not apply? Rolle's theorem doesn't apply, okay? So Rolle's theorem does not apply. Now, if I change the interval from negative 8 to 8 to something else, maybe a smaller interval, do you think it could?
Yeah.
If I change the interval to, let's say, 2 to 8, could we apply Rolle's theorem?
Yeah.
I agree with you. Why is that?
After 0.
Yeah, it does. From 2 to 8 does not contain the cusp or the point of differentiability. Okay? Who's with me so far? Okay. Now, let's go to the next page. Oh, holy cow. Back up for a second. Sorry guys, I have to make a modification here. I just noticed something. Surprised you guys didn't say anything. Go back up to the theorem. I'm going to have to redo this video, but I'm going to continue. We talked about being differentiable on the open and continuous on the closed, but what else do we have to check? We have to check if f of a must be. Okay, and I didn't do that, did I? Okay, yeah, it's because I don't know, I just missed it here. So go back to example 1. We got to check that. So it's part of the check in part A. We also have to check if f of a equals f of b. All right, is that the case or is it not? If it's not the case, then we're not going to apply Rolle's theorem. So let's do that. We have to check f of 0, get a number, and then f of 2, and they better be equal. If they're not, then what I said was bogus. Okay?
That goes back to the original equation.
Well, what is f? If f is f the original function?
Oh, yeah.
I didn't say f prime of a, I said f of a, right? So let's go back there and let's do it. Let's take 0 squared minus 2 times 0. What do you get? 0. Let's check the other one. 2 squared minus 2 times 2. Okay, so this tells you that f of 0 equals f of 2. That combines with my statement up at the top, the polynomials are continuous and differentiable everywhere, combined with this right here, imply what about Rolle's theorem? It applies, okay? So Rolle's theorem applies. So my apologies on that one there. This one gets violated right off the get-go. We didn't have to check FA and F of B because it wasn't differentiable on that open interval.
How would you find C?
We did that already. So we set the derivative equals 0 and solved it.
All right.
That's all you do. Okay? Okay, now what happens if f of A is not equal to f of B? Let's turn the page and let's talk about what's called the mean value theorem. Okay, let's read at the top together. This is why they're related, the two theorems. You see, f of A and f of B may not be the same. Okay, read up here at the very top. We now let f of A and f of B have other values than f of A equals f of B. Suppose they're different. Let's suppose they're not equal to one another. Then what do? Okay, so if that's the case, we still expect, and let's take a look at the graph up here. If we have a function here, call it f. This is our function f here. We expect in the open interval from A to B, there exists some c. Look up here now, come on. There exists some c such that the slope of the tangent line, which in this case is this one up here, this is f prime of c. You know, that slope's not 0 because it's not horizontal. We expect there to be some c in between A and B so that the slope of the tangent line is equal to the slope of this line right here. Now, what do you call a line that intersects a function twice? A secant line. Okay? So we expect the slope of the secant line to be equal to the slope of the tangent line at some point C, and where's C? In between A and B. Okay, so it's a different generalization of the Rolle's theorem. Here's f of B, and who sees that f of B is different than f of A? Which one's bigger?
F of B.
In this case, f of B, because it's higher, right? So what I'm saying is this. Let's go down and let me formally state the mean value theorem right here. Okay, it's similar to the Rolle's theorem. Just check out the hypothesis. F has to be differentiable in the open. That's the same. And continuous where? On the closed. So this is closed, and this is open. Right? And then here we go. Here's some important words. There exists at least one C. What does that mean? One or more. Okay, one or more. So we'll see some cases where there are 2 or 3 of them. Okay, one or more point C in A, comma B, which means the open interval from A to B, for which the slope of the tangent line, in this case right here at C, here's f prime of C, is equal to the slope of the secant line in orange color up there. So the slope of the tangent line, which is f prime of C, must be equal to the slope of the secant line. So we've done this before, but a long time ago. How do you find the slope of a secant line? And how do you do it in Algebra 1? So how do you define slope in general? It's rise over run. Okay, but more importantly, isn't it y2 minus what? y1 divided by? Okay, so let's figure that out. Okay, so here we go. I's at A on the x-axis here. Let's go up to the function, move left. What should this value be? f of a. Very good, Brandon. F of a. I's of b now. I's of b, go up to the function, move left. No. What's that? F of b. All right. So we want to find the slope of the secant line. So what you do is you apply the definition of slope right here. You take this y value, f of b, subtract what? F of a. You got to get your rise, right? The rise from f of a to f of b is the difference between the two. So f of b minus f of a divided by the difference in the x values right here. And what would that be? B minus, well, you always go right minus left, so b minus a. So we have f of b minus f of a, all right, divided by the difference in the x values, b minus a. This right here is called the slope of the secant line. What's f prime of c stand for? Slope of what? Slope of tangent line. So slope of the tangent line. Somewhere between a and b, there's got to be a value of c such that the slope of the secant line is equal to the slope of the tangent line. In fact, in this graph right here, there's another value c. I'll call this one c1. Who sees another one?
Oh, okay. Yeah, right under y.
Who sees a relative max up there? Is it near the relative max? You tell, let's see here. Let me get a pencil or a ruler here. We want the slope of the tangent line right here to be equal to the slope of the secant line here. So tell me when to stop. Who says C right here? Here's the second value of C. Who's with me on that? Okay, let's draw this line in. See, there's in some graphs, depending on the slope of the function, there may be more than one C value. So right here, we'll call that C2. So C1 and C2, so this right here is f prime of C2, and that's equal to, some slope. But it's going to be equal to the slope of the secant line. So our job right now is to find those C values between A and B so that the slope of the tangent line is equal to the slope of the secant line. That's what the mean value theorem is all about. Okay? And we have to do the check. We have to make sure it's differentiable on the open and continuous on the closed, and if so, we can find C. So we're going to do that similar to the Rolle's theorem. But this time, f of A and f of B are clearly not the same. They're not equal. So we don't have to make that check like we did the Rolle's theorem. All we have to do is check to see if it's differentiable on the open and what? Come on, guys. Differentiable on the open and?
Oh, and the close.
Continuous on the closed, and then we're good to go. So here's what we got to do, and then it becomes a three-step procedure. Look right here. We have to evaluate a what? We have to evaluate a derivative.
Okay.
It's called a derivative, guys. F prime is called a derivative. We have to evaluate a derivative, and then we have to evaluate slope of the, which means we've got to calculate these values here and calculate this. And then step 3, you got to set them equal and solve for C. Where's C? Where's C? In between A and B. Okay, whatever value C is not inside A and B, you disregard it and take the ones that are inside. Okay, so here we go. Let's check it out. Okay, so we got a root function. I even give you the graph right there. Okay. Now look at the graph and look at the root function here, and let's talk domain because you're going to have to think domain when you do this because sometimes the graph's not provided. And if you don't have a TID4 or if the graph's not provided, you have to talk domain. Okay. So the root functions are all continuous on their domain. And what's the domain of the root of 2 minus x? Let's write that down over here. Domain. How do you determine the domain of the root function there? Yeah, if x is greater than 2, you end up with what kind of number inside the root?
Imaginary.
Imaginary. So here, all you have to do to figure out root questions or domain questions is make sure that the radicand, all that stuff underneath the root, is greater than or equal to 0, and solve that equation. That's all you have to do, and there's your domain. Any kind of root function, just set the stuff underneath the root greater than or equal to 0 and solve it. Like this implies that 2 is greater than equal to 0, greater than equal to x, correct? By adding x to one side? Now reverse the inequality, what do you get? If 2 is greater than equal to x, then x must be, there's your domain. Okay, now look at your closed interval. Your closed interval right here is from -7 to 2. This function is defined everywhere less than or equal to 2. It's continuous and differentiable everywhere less than or equal to 2. Is that closed interval in that domain? Is -7 to 2 is less than or equal to 2? Okay, so then there you go. So since we're dealing with a closed interval from -7 to 2, it's continuous and differentiable in that interval. So we're good to go. So you got to state that though. This is part A. So f is continuous, okay, and differentiable, okay, on the closed interval from -7 to 2. Because we took a look at the domain, we analyzed it. Because like I said, you're not always going to have the graph. You're going to have to look at the domain of the function to determine that. Okay? Now because we satisfied the first part of the theorem, we get to go for it. So part C, we got to find C. But before we do, we have to find a derivative. So first step is differentiate. So f prime is equal to, let me see, f is the same thing as 2 minus x to the 1/2 power, right? So is this a straight power rule problem, or do we have to kick in the chain rule? Chain rule as well, okay? So the outer function first. So here we go, 1/2 times the derivative, or excuse me, times 2 minus x to what power? -1. 1/2 minus 1 is -1. Times the derivative of the inside.
-1.
Very good. Derivative of 2 is 0. Derivative of negative x is -1. Let's rewrite. -1 divided by 2 times the square root of 2 minus x. There's f prime. Okay, that's step 1. You got to find the derivative. Step 2. You got to find the slope of the secant line. Step 2. Find the slope of the secant line. Slope of secants. And that's equal to f of a minus f of, well, it's f of b minus f of a all divided by b minus a. Okay? But in general, you're looking at a is here and b is here, yes? So it's f of what? F of 2, f of b, f of 2 minus f of a, f of -7, all divided by what minus what? B minus 2 minus a -7. That's f of b minus f of a, all divided by 2 minus -7. So what's f of 2? We got to do our homework. So f of 2, you got to help me out a little bit. F of 2 is 0. F of -7, what's that?
3.
It's the square root of 2 minus a -7. That's the square root of 9. That's equal to 3. So here we go. This step's not that bad. So we got 0 minus 3 divided by 9. What's that equal to? -1/3. What does that represent? The slope of the secant line. Now Rolle's theorem states that the slope somewhere in between a and b there exists a c, at least one, such that the slope of the tangent line, which is right here, it's this derivative, is equal to the slope of the secant line, which is equal to -1/3. So what do we need to do with these two steps? We set them equal to each other. Okay, so step 3, we set them equal. So step 1, step 2, step 3 here. We got -1 divided by the 2 times the root of 2 minus x is equal to -1/3. We got to solve that equation there. So right off the bat, both sides are negative, yes? So cancel out the negatives. And you guys know this fact about proportions, that if you're looking at it, I mean, you can cross multiply if you want, or you can just reciprocate both sides. You guys know that property? If you have 2 equal fractions, the reciprocals are also equal, yes?
No, yeah.
Yeah, so just reciprocate both sides and you get something a lot easier to handle. You get 2 times the root of 2 minus x is equal to what? 3. What do you think the next step should be? Okay, you can divide by 2, or you can do what right now? You can square it. If you square both sides, what do you get? On the left, what do you get? 4 times 2 minus x is equal to 9, and then, just keep on going. 2 minus x is equal to 9/4. Subtract 9/4 and add x, you get 2 minus 9/4 is equal to x. Let me see, 9/4, what's that?
2 1/4.
So 2 minus 2 1/4, what's that? Negative 1/4. Okay, now, this must be in the open interval from negative 7 to 2.
Yeah.
Is it in the open interval?
Yep.
Okay, let's say in the open interval from negative 7 to 2, and because of that, that's C. So C equals negative 1/4. We found it. Remember to check this. A lot of people forget to check this, because sometimes your values of C you get like 2 or 3 of them, and some are inside here and some are not. So we take the ones that are inside the interval and throw out the ones that are outside. Give me a show of understanding so far today. This is full, pretty good, not so good. Where are you at? It's not bad overall. I know it takes a little bit of time and practice. Don't worry about it. It always takes practice. Let's go over the steps. Look right up here. Step 1, what do we do? Oh yeah, okay, see if Rolle's theorem applies. That's our actual step 1, okay? But in terms of finding C, what's step 1 here? Okay, take a derivative, differentiate. Step 2, we find the slope of the secant line, and in general, that's f of b minus f of a, all divided by b minus a. You figure out what that is, do some work on the side. And step 3, we set them equal. You do what? Sorry, but I didn't mean to give that away. You set the slope of the tangent line equal to the slope of the secant line, and you solve. And whatever values you get, right there, there are possible values of C. Which ones do you take? Ones that are on the open interval. What does that mean? They must be, they must be between A and B. Okay? God, I got to hold back. Okay. All right? So let's try it again. Okay. Now, you need some experience because there's like 3 main functions. There's polynomials you're going to be working with. They're pretty easy. There are root functions. They're a little bit more difficult because the domains are not the set of reals. And then there are these kind of rational functions here where they're discontinuous somewhere. And so what you always want to do is look at the points of discontinuity, basically where the function's undefined. So take a look at that rational function up there. Tell me where it's not defined. Okay, so the domain is all reals except what? Negative 1. Is that a non-removable discontinuity, like an asymptote, or is that a whole? Asymptote or whole? Okay, if it was a whole, it could have been removed. So this is a non-removable. So we have an asymptote at negative 1, a vertical 1. Yeah, that's it's discontinuous there. Now the mean value theorem can only be applied if it's continuous everywhere and differentiable on the open. So my question is to you is it differentiable on the open and continuously closed on that interval from negative 1/2 to 2? Not everywhere, but on that specific interval. Yes. Give me a vote, yes or no, or this means not sure. Okay, everybody's saying yes because negative 1 lies outside the interval. The point of discontinuity is outside the interval, which means it's continuous in the interval, not outside the interval. You guys with me on that? Got to write it down. Okay, that's part A. So here we go. So determine whether it applies. So we say that since f is let's see, since f is not defined or not differentiable at x equals negative 1 outside the interval. Outside, well, I'll just say this right here, outside negative 1/2 to 2. Okay, it's non-differentiable at negative 1, but it's outside the interval. It must be continuous inside and differentiable on the inside. I could have written this a little bit better here. It is continuous, okay, and differentiable on that closed interval. Keyword there was outside. So I should have written that a little bit better. Okay, I should have said something like it's continuous, or it's discontinuous outside the interval, so therefore it must be continuous inside the interval, and differentiable in the interval. Okay, so we're good to go. Rolle's the mean value theorem, MVT for short, applies, and if it applies, we can go to step part B. Ooh, this one, you know what? We got 3 parts here. We got to find C and then find the equation after that. We got some work to do on this one. Okay, so it's a 3-step process. Going back up to the previous problem, we got to differentiate step 1. Step 2, we got to find the slope of the tangent line, and then secant line. Thank you. And then way to be alert. And then step 3, we set the slopes equal, and then we solve for that equation here, or solve for that value. Okay, so we need to differentiate. So what rule do we need to use here, guys?
Quotient.
That's right, a quotient rule. So f prime. Okay, we got to take x plus 1 times the derivative of x, which is 1, minus x times the derivative of x plus 1, which is 1, all divided by x plus 1 squared. Hey, that's nice. What does that simplify to? Say it out loud. Oh, don't the x's cancel out?
Yep.
So what's the numerator? 1. So 1 divided by the quantity of x plus 1 squared. Okay, I heard some different answers there. Okay, so we got that. Step 2, we got to find the slope of the secant. Okay, and that's f of 2 minus f of negative 1/2, all divided by 2 minus a negative 1/2. I'm going to pause the video, go ahead and start working on that now. Okay, as a class, what'd you get for f of 2? I agree with that, 2/3. How about f of negative 1/2? I agree with that too. So minus a negative 1, all divided by 2 plus a half, which is 2.5 or 5/2. I'll write it instead of 2.5, I'll write it as 5/2 because you have to multiply by the reciprocal in a minute. And 2/3 plus 1 gives you 1 2/3. Well, what's 1 2/3 is an improper?
5/3.
So you have 5/3 divided by 5/2. You multiply by the reciprocal, 5/3 times 2/5. What's that? 2/3. Who got that part right? Okay. You just multiply by the reciprocal and you get 2/3. That's the slope of the secant line. Now we're trying to find C between A and B, so that the slope of the tangent line in step 1 is equal to the slope of the secant line in step 2. So now we want them equal. All right, so now set them equal. You got 1 divided by the quantity of x plus 1 squared is equal to 2/3. And you got to solve that baby. Okay, I'm just going to reciprocate. So x plus 1 squared is equal to 3/2. So just reciprocate both sides, and now what?
Square root.
Square root. And you get x plus 1 is equal to plus or minus, and then you gotta rationalize this puppy. What's it rationalized? What's the numerator here, guys? Just look right here. What's the numerator?
6.
Not 6, but come on, guys. 3 times 2 is 6, but you got to root it.
Oh, root 6.
You guys are looking at me like I'm doing.
Root 6 over 2.
You guys, root 3 divided by root 2. And come on, rationalize. You get root 6 divided by 2. You guys looked at me like I was doing some serious mathematics up here. Wow, yes. When in proportions, like if you have A to B equals C to D, that's equivalent B to A equals D to C. You just reciprocate both sides. And the reason why I did that is because, look at this right here. Look at that 1 over x plus 1 squared. If I reciprocate it, you just get the numerator, right? And reciprocating 2/3 is 3/2. Just simplifies things. So plus or minus root 6 divided by 2. So x is equal to negative 1 plus or minus root 6 divided by 2. Okay. How many possible values of C do we have? 2. Well, let's write them separately. Negative 1 plus root 6 divided by 2, and negative 1 minus root 6 divided by 2. These have to be where? In between what? What's our interval? Between negative 1/2 and 2. So they have to be in the open interval from negative 1/2 to 2, in between those two values. Can't be the endpoints. It's got to be between. So which one's between? So we need to figure that out. By the way, it should be obvious. Like this right here, negative 1 minus root 6 over 2. Who sees that's to the left of negative 1?
Yeah.
I mean, I don't know what it is, negative 1 point something, right? Or negative, we'd have to figure it out, but it's to the left of negative 1, so who sees that it's not in the open interval here? Okay, so this one's not acceptable. That's not a C value. This one is if it's inside here. Okay, it is, but I want you to check it. Use your calculators right now and evaluate that and get a decimal. Okay, so you guys get a decimal yet? So negative 1 plus root 6 divided by 2. Make sure you put a parentheses around the 6. Give me a thumbs up if you agree with that. Okay, is that in the open interval or in between negative 1/2 and 6?
Yeah.
It sure is. So let's just record that value, 0.22. Okay, this is inside. So this is our C value right here. C equals negative 1 plus root 6. Whoops, root 6 divide. Oh, come on. Let me rewrite this here. Negative 1 plus root 6 divided by 2. Okay, and now you're going to have some fun, and you're going to have to find the equation line at C. You know, because, let's just set up. Let's finish up the problem. Okay, last part, part C. Find the equation of the tangent line, and then we're done. Okay, we're only one step away. We know the slope now. What's the slope of the tangent line? Oh, but that's the slope of the secant line. But what do we know about the slope of the tangent line in respect to the slope of the secant line? They're what? No, they're not reciprocals. They're equal. Okay, so the slope of the tangent line is also 2/3. Okay, so let's go down and use it. So here we go. Y minus y1 equals m times x minus x1. All you have to do is put in the slope, put in your point, and you're good to go. So what's our point of tangency, though? Holy smoke, you know what we got to do? You got to plug C back into the function. What do you mean it's right there? Yeah, I know, it's right there. Yeah, but C comma what? It's oh man, I made a gnarly one, didn't I? I got to make an easier example next time. But what you have to do is you have to substitute your slope in, and then you'd have to find your y value. And we know our x value. It's negative 1, plus root 6 over 2. All right, but to get your y value, you got to substitute C back into the function and evaluate your function. But I got good news for you. Okay? I'm going to have to change this example for my next year, because this is way too difficult. But you're going to have one like this on your homework, and which you're going to have an easier value. It's going to be like 2. C is 2. And then what you're going to have to do is get your y value. You're going to have to plug that back into the function, evaluate, and go one step further. Who's with me?
I'm with you, Edgeworth.
All right, who's going to do the homework tonight?
I'm doing homework, Edgeworth.
All right.